Hello everyone, welcome back to my YouTube channel. In this week's video, we are going to discuss 6 different questions ranging from chapter 5 till chapter 7. So let's get started. Question number 1. The Ka of a chlorous acid is 0.010. It is predicted that the pH of 0.1 molar of chlorous acid in aqueous solution at equilibrium is 4. Explain if this claim is correct. In order for you to answer this question, the first thing you need to do is to write a balance equation for this reaction. So what we need to do is we need to write the dissociation reaction of the chlorous acid. So basically the chlorous acid, because it is in aqueous solution, so we need to add water. It is a reversible reaction. Therefore, we shall get, it shall dissociate into ClO2 minus plus the hydroxonium. So apparently this is the balance equation, and the next thing we need to do is we need to write the ice diagram. So in the ice diagram, the first thing that we need to look at is what is the initial concentration. So given in the question, the initial concentration is equivalent to 0.1. In the ice diagram, we shall not look upon the water, so we just leave it as is, and there's no product should be formed in the initial state. So at change, here will be negative X, positive X, and positive X. Therefore, at equilibrium, it shall be 0.1 minus X, X, and X. Looking at the question, we can see that the value of Ka is given to us. Therefore, Ka is equivalent to X times X divided by 0.1 minus X. Given to you, the Ka is equivalent to 0.010. Therefore, it's equivalent to X squared divided by 0.1 minus X. So what we are going to do now is we are going to do approximation method. In approximation method, it's going to be 0.010 is equivalent to X squared divided by 0.1, whereby we shall omit this X. So X squared is equivalent to 0.010 times 0.1. Therefore, your X is equivalent to the square root of 0.010 times 0.1, and you shall get value of X is equivalent to 0.0316. Alright, next up, what we are going to do is to determine whether the value of X that we calculated just now is okay to be used or not. Alright, so we are now going to do the test. So test is equivalent to value of X divided by the initial concentration times 100%. So basically the value of X is equivalent to 0.0316 divided by the initial concentration. So the initial concentration is here. So divided by 0.1 times 100%. Therefore, we should get 31.6%. So this value, 31.6%, is actually bigger than 5%. So fail. Right? So since we failed this test, what we are going to do is we are going to substitute back the value of X to the one that we omitted in the approximation method. So we are just going to calculate again the value of X. So Ka is equivalent to X squared divided by 0.1 minus X. So this is the initial one. So before this, we remove the value of X. So now we are going to substitute that value of X with the value of X that we calculated. So given in the question, the value of Ka is equivalent to 0.010. So x squared is divided by 0.1 minus the value of x, 0.0316. Therefore, we should be able to get the new value of x. So x squared is equivalent to 0.010 times 0.1 minus 0.0316. Therefore, we will get x is equivalent to square root of 6.84 times 10 to the power of negative 4. Therefore, your x is equivalent to 0.0262. So, from here, you do not need to make a test check again. We are going to use this value of x as is. Okay, so moving on, we are going to look at the question again. It is predicted that the pH is equivalent to 4. So in order for you to know the pH, you need to know what is the concentration of your hydroxonium. Therefore, your hydroxonium is equivalent to X. So the concentration of your hydroxonium is equivalent to 0.0262. So from here, we can get what is the value of your pH. Alright, so from the previous calculation, we found that the value of X is equivalent to 0.0262, whereby the concentration of your hydroxonium is equivalent to X, which is this value. Therefore, in order for you to find the pH, is equivalent to negative log H3O plus. So since you already know what is the concentration of your H3O plus, so we are just going to plug in the value. So negative log 0.0262. Therefore, you should get your pH is equivalent to 1.5817. So this is your pH. So in the question, it predicted that the pH is equivalent to 4, but supposedly the answer is 1.5817. Therefore, the claim is incorrect. Alright, so this is the final answer for the first question. Let's move on to question number 2. In an electrolytic cell, a redox reaction is made to occur by supplying electrical energy to the system with copper and iron electrodes. Determine the standard free energy change, delta G, of the reaction. Given that the standard reduction potential of copper 2 and iron 2 are 0.34 volt and negative 0.45 volt respectively. In this question, the most important information given to you is the standard reduction potential. And you need to remember that the more positive the standard reduction potential, in this case this one, it shall be at cathode. And in cathode, it shall undergo reduction reaction. So now what we are going to do is we are going to write the half reaction and the overall reaction for this specific reaction. So we will have anode, we will have cathode, and the overall reaction. So what we are going to do now is we are going to start with cathode. At cathode, it will have a more positive standard reduction potential. So this is meant for copper, and it shall undergo reduction reaction. So copper 2. So here given to you is copper 2. So since it does reduction, so we need to start with Cu 2 positive plus 2 electron. It shall produce the copper in solid form. Alright, so moving on to the next one, you have iron 2, but the iron 2 is going to be oxidized. So it means that the oxidation number shall increase. So it shall start with iron, it's just iron, and then it will be iron 2, So you have 2 electrons over here. So at the overall reaction, we shall have iron plus copper in ionic form, and here we will have Fe2 plus Cu, because here you can already remove the electron. So what we are going to do next is we are going to put what is the E cell. So given to you here is negative 0.45 volt for the reduction reaction for ferrum, for iron. So since that this undergoes oxidation, we are going to change it to positive 0.45 volt. So for copper, it does undergo reduction. So we are just going to use the value as is, 0.34 volt. Therefore, at the overall reaction, we're just going to do the summation of this value. So you should get 0.79 volt. And then you can also calculate this as the anode cell. Is 0.45 volt plus 0.34 volt, therefore you will get 0.79 volt. Right, so this is the first part of the calculation, and you were asked to calculate what is the standard free energy, which is the delta G. So for the delta G is equivalent to negative NF anode, so anode cell. Alright, so your N is actually the number of electrons. So we have 2 electrons, so your N is equivalent to 2. So what is F? This is a constant value, so you need to remember the value of F. So it's 96.485 kilojoule per volt. And then the anode cell is the one that you have just calculated. So you just have to plug in that value, 0.79. Therefore, you will get your delta G naught is equivalent to 1.5245 times 10 to the power of 2 kilojoule. So this is the final answer for the second question. Question number 3. A balloon is filled with helium gas at pressure of 1.1 times 10 to the power of 5 Pascal with a temperature and volume of 25 degrees Celsius and 6.5 times 10 to the power of 4 centimeter cube respectively. Calculate the average translational kinetic energy of helium gas inside the balloon given that the Boltzmann constant is equivalent to 1.3807 times 10 to the power of negative 23 joule per Kelvin per molecules. Alright, so if we look closely at the question, we see that there are certain units that is not in the unit that we want. So for instance, we have pressure in Pascal, temperature in degrees Celsius, and the volume is in centimeter cube. So the first thing that we need to do is we need to convert all these units into the correct unit. So I'm going to start with the pressure. So we have 1.1 times 10 to the power of 5 Pascal. So when we want to convert it is 1.1 times 10 to the power of 5 divided by 1.013 times 10 to the power of 5. Therefore, you will get 1.0859 atm. But if you want to convert it directly from your calculator, you can do so as well. So moving on to the temperature, we have 25 degrees Celsius. So we just need to plus 273. So you will get 298 Kelvin. And the last one is 6.5 times 10 to the power of 4 centimeter cube, which is milliliters. So you want to convert that to a liter, you need to divide with 1000. Therefore, you will get 65 liter. So from all these values, what you can do is you can find what is the number of mole. Because in order for you to calculate the average translational kinetic energy, you need to know how many moles and how many molecules are there in this helium gas. So because you were given the Boltzmann constant, so therefore you should always calculate what is the number of molecules available in this helium gas. So the perfect formula that we can use in order for you to find what is the number of mole is the ideal gas law. PV is equivalent to nRT. So PV equivalent to nRT, the P is 1.0859 and the volume is 65 liter, and is the one that you want to calculate. R is the gas constant 0.0821 and your temperature is equivalent to 298 Kelvin. Therefore from here we can get your N is equivalent to 70.5835 divided by 24.4658. Therefore you will get the number of mole of helium gas is equivalent to 2.8850 mole. Alright, so since you were given the Boltzmann constant, what we are going to do is we are going to convert this number of mole into the number of molecule. So in terms of converting it, you just have to find the number of molecule by multiplying the number of mole times the Avogadro number. So the number of mole is 2.8850 times the Avogadro number is 6.0221 times 10 to the power of 23. Therefore, you will get 1.7374 times 10 to the power of 24 molecules of helium. Alright, up next, we are going to use this value and associate it with the Boltzmann constant to find the average translational kinetic energy of helium gas. Right, so the formula for the average translational kinetic energy is equivalent to KE RMS is equivalent to 3 over 2 N, which is the number of molecules, K, which is the Boltzmann constant, and T. So now we're just going to plug in the values. So we have your KE is equivalent to 3 over 2. Your N is this value, 1.7374 times 10 to the power of 24 times your K, which is the Boltzmann constant given to you in the question, 1.3807 times 10 to the power of negative 23 times your temperature. So your temperature is 25 degrees Celsius. We already converted to Kelvin, so 298 Kelvin. So here is molecules. The unit here is joule per Kelvin per molecule. So that one is K. So looking at this unit, so molecules and molecules, here is Kelvin and Kelvin. Therefore, we can say that your kinetic energy, the average translational kinetic energy, which is the KERMS, so it's equivalent to 3 over 2 times 7.1485 times 10 to the power of 3. Therefore, you will get 1.0722 times 10 to the power of 4 joule. So this is the final answer for this question. Alright, so this is just an additional information. If you have already calculated the average translational kinetic energy, how are you going to ensure that your calculation is indeed correct? So the first formula is the KE RMS, so it's equivalent to 3 over 2 and KT. So from here you will have 3 over 2 Your N is 1.7374 times 10 to the power of 24. So this one is molecule. And then you will have your Boltzmann constant, 1.3807 times 10 to the power of negative 23 joule per Kelvin per molecule. And then you will have your temperature 25 degrees Celsius. You convert it to Kelvin to 198 Kelvin. Therefore, you will get 1.0722 times 10 to the power of 4 joule. Right? Because for this part, molecules, Kelvin and Kelvin. Okay, how are you going to check whether your answer is correct or not? So you can use another formula. KERMS is equivalent to still 3 over 2, but instead of NKT, you can use NRT. So 3 over 2, your N now is not the capital N, but it's the small n, the number of moles, so it's 2.8850. Your R, make sure that you use the correct R. You need to have it in joule, so 8.3145 joule per Kelvin per mole, because this one is already in mole. And then your T is 298 Kelvin. So the same drill, so you have mole here, you have mole here, Kelvin, Kelvin. So if you calculate this value, you should get the same as this, which is 1.0722 times 10 to the power of 4 joule. So this is how you check whether your calculation is correct or not. Alright, so let's move on to question number 4. 100 centimeter cube of water was heated until it reaches 212 Fahrenheit. Calculate the viscosity of the gas released from the kettle spout using the Sutherland's formula. Right, in this question, the temperature is in Fahrenheit. So the first thing we need to do is we need to convert this to degrees Celsius. So TF, which is in Fahrenheit, is equivalent to 9 over 5 temperature in degrees Celsius plus 32. So you will have the temperature in Fahrenheit is 212 is equivalent to 9 over 5 Tc plus 32. Therefore, your temperature in degrees Celsius is equivalent to 100. Alright, so after that, because you were asked to use the Sutherland formula, so you need to use it. So the viscosity is equivalent to, over A over B, so times T over T naught to the power of 3 over 2. Right, so next up, what we are going to do is we need to calculate what is A and what is B. So A is basically 0.555 T naught plus C, and your B is equivalent to 0.555 T plus C. Alright, so what is T naught and what is T? Okay, so your T is equivalent to the value of T that we already calculated just now, which is in degrees Celsius. But for your T naught is from the table. So from the table, the nearest to the value is 100 as well. So means that your T and your T naught is equivalent to 100 degrees Celsius. And then what is C? So C, you need to look at the information given to you in this table. So if you look at the question first, it states here that the water is heated until it reaches 212 Fahrenheit. So 212 Fahrenheit is 100 degrees Celsius. So you need to realize that at 100 degrees Celsius, the water shall turn into steam. Therefore, here you need to look at steam, and then the value of Sutherland constant, which is C, is equivalent to 260. Therefore, from the calculation, we can get the value of A and B, both are the same, which is equivalent to 467.0150. So this is the value of A and B. So now you already know what is the value of T and T naught. So what we need to do is we need to plug in the value inside. Therefore, from this, we will get your viscosity is equivalent to 0.0124, which is your mu naught. So in case you're wondering where did I get this value, it's from the table as well. So you look at your T naught is 100 degrees Celsius and you look at steam. Therefore, your mu naught is equivalent to 0.0124, right? So next, you need to divide A over B. So since this is the same value, so A over B is equivalent to 1. And then your T over T naught, so still equivalent to 1 because both are 100 degrees Celsius, to the power of 3 over 2. So you shall get the mu is equivalent to 0.0124. Therefore, this is the final answer for this question. Let's move on to question number 5. A reaction at 57 degrees Celsius has a rate constant of 0.5 per second and activation energy of 25 kJ per mole. The identical reaction was conducted by increasing the temperature by 70 degrees Celsius from the initial run and the reaction reset. Determine the new rate constant at the new temperature. Alright, so the first thing that you need to look at is the temperature rise. So identical reaction was conducted by increasing the temperature by 70 degrees Celsius from the initial run. So initial run, the temperature is 57 degrees Celsius. So do not use 70 degrees Celsius, but you need to do 57 degrees Celsius plus 70 degrees Celsius. Therefore, at the run that we are going to look at is actually being carried out at 127 degrees Celsius. Okay, another thing that you need to look at is the activation energy is 25 kilojoule per mole. Therefore, this one, 25 kilojoule per mole, you need to convert to joule per mole. Therefore, you should times 1000. So you will get 25,000 joule per mole. Alright, so once we already converted all this into the correct unit, so we can plug in this value inside the correct formula. So we have ln K1 over K2 is equivalent to activation energy over R times T2 minus 1 over T1. Okay, now we just have to plug in the value. So ln K1, so the K1, the rate constant is 0.5. So 0.5 per second over K2, the one that we want to calculate. And the activation energy, we already converted it to 25,000 joule per mole. And around here, R is the gas constant. So the gas constant is 8.3145 joule per Kelvin per mole. And then the temperature. The second temperature is this one, 127, because here is in Kelvin, plus 273 minus the initial temperature, which is 57 plus 273. Alright, so from here we can see that this is joule. You can slash this out, and then mole also you can do so, and here shall be in Kelvin, so it's going to slash through over here as well. So now we're just going to calculate the value. So I'm going to convert this part first. So ln 0.5 per second over K2 is equivalent to 25,000 over 8.3145. So this one times 1 over 400 minus 1 over 330. So from this calculation, you should get ln 0.5 per second over K2 is equivalent to negative 1.4945. There will be no unit for this. And then now we're going to make this into ln. So ln 0.5 per second minus ln K2 is equivalent to negative 1.5945. Therefore, we are just going to bring this to the other side. Ln K2 is equivalent to negative 1.5945 minus ln 0.5 per second. So you will get K2 is equivalent to 9.0135 times 10 to the power of negative 1. Therefore, K2 is equivalent to 2.4629 per second. So this is the final answer for the fifth question. Alright, let's move on to the final question for this week's video. Consider the reaction between the butadiene. So the reaction is following the second order reaction with a rate constant of 5.76 times 10 to the power of negative 2 mole per minute under a certain condition. If the initial concentration of butadiene is 0.2 molar, identify the concentration after 600 seconds. Right, so the first step that you need to do is look at the unit given. So the rate constant is in molar per minute, and then the time given to you is in second. Therefore, you need to convert this into minute. So 1 minute is 60 seconds, so 600 you need to divide by 60. Therefore, you will get 10 minutes. And then what else is given to you in the question is it is a second order reaction. Therefore, in the second order reaction, we are going to use the formula of 1 over AT is equivalent to KT plus 1 over A naught. Right, so what is the AT and what is the A naught? So when we want to calculate what is the AT, because it states here the initial concentration is 0.2, so your A naught is 0.2 over here. So identify the concentration after 600 seconds. So you were asked to calculate what is AT. So K is given to you in the question. So you already have the value of K, and it is 10 minutes, so you already have the value of T. So since we already have all the value that we needed, so we can calculate your AT is equivalent to K, which is 5.76 times 10 to the power of negative 2 molar per minute times your T is equivalent to 10 minutes plus 1 over A naught, which is 0.2 molar. Right, so from here, this one is per minute and this one is minute, so you are left with molar. So from the calculation here, you will get 1 over AT is equivalent to 5.576 molar. Therefore, you will get your AT is equivalent to 0.1793 molar. So this is the final answer for the sixth question. Alright, so we have come to the end of this week's video, which is the final video that I'll be posting for this semester. So I wish you all the best for your final examination. Take care and be good. Goodbye.